I'm Rhea.
I'm on Pablo.
And I'm Gabby.
And we're
Teens Tutor Teens.
Hey guys, today we're going to be learning about the unit circle and some applications of this. And I specifically love this unit because, well, everything's a circle here. It just revolves on mini triangles that people make and stuff and things like that in that order. So let's get started with what the unit circle is. So basically the unit circle is kind of like this cool diagram. Okay, it may be hard to read at first, but if you think about it, you can like point out the unit circle by looking at the dots like, okay, that's going to be 0, that's 0, 1, that's negative 1, 0, and that's 0, negative 1. And you can notice that like the range, so if you guys remember, like range is how high it goes on the y-axis. It's going to be from negative 1 to 1, including that, to 1. And then the domain is going to be including negative 1 to 1. So it goes on both sides like that. And so it keeps everything inside a unit. And then these numbers that you see in here are going to be greater than 1, but they can be less than 1. But not, you know what I'm saying? And they can be in a sense less than, well, actually greater than negative 1, but they can't be less than negative 1. So that kind of goes along with the range and domain we were talking about here. Anyways, so how you read this is you can either read it going this way, where you're going to have angles and degrees, radians, whatever you like to use that are positive, or you can read it going backwards with the negative. So just for today, let's just focus on using it more with positive kind of values. I feel like that's a little bit more generally easier, so right here. And okay, so how this works is they give you the angles kind of inscribed right here below, so you can see like that's 30, that's 45, that was 60, and that's 90, and there's some cool property that goes along with this. Here are the degrees, but here is where it says in radians what it is. Now with radians, you don't actually use this degree sign, you just put it as in terms of pi. So this whole entire thing would be 2 radians because going halfway would just be pi, but whole round would be 2 pi rads. That's how they use it in short term. But people also use degrees and they just say 360 degrees as well. I mean, both ways are fine. Both ways. Or you can say it's 0 degrees, like I'm saying again. So let's see this triangle that we're gonna make here, okay? And let's just say it's 45 degrees. Let's just use degrees today. Because usually everyone uses degrees around, geometry and such. To go to pre-cal even. And even they use these degrees a little bit, but sometimes they're going to transition to radians. So 45. They're telling us that x is going to be square root of 2 over 2. And y is going to be square root of 2 over 2. Now, if you were to use the Pythagorean Theorem, you would find out by squaring both of these now together, like a squared, remember, plus b squared equals c squared, where this can be told as a, this is b, so c is right here. C would actually equal 1. Just like, again, one of the coolest things about the circle, because like we said, the magnitude of the maximum value is 1. Okay? We already defined that when we were talking about range and domain right over here. So that's why it makes a little bit of sense. So now we're going to erase this board, and I'm going to show you some cool properties about this and talk to you more about this unit circle. Okay, so now that the board is erased, I'm going to show you some things you may have seen before. Sometimes you're going to be asked to find the sine of something, the cosine of something, and the tangent of something. So looking at this triangle here, okay, and let's just call it D, let's call this side A, let's call this side B, dab. Okay, now let's figure out the sine of this. Sine of what? Theta. That's the thing that we always have to establish. I'm going to show you where theta could be in 2 ways. So we're just going to call the black theta right here. We're going to call the green theta we're going to do later on and right there. So the sine of black theta is opposite over hypotenuse. So you have to look opposite, which is A. The hypotenuse is the longest side on this triangle. And we've already discovered in our previous example that, remember, these two sides are usually going to be, the legs, is usually going to be overall shorter if it's contained in a unit circle and such. Or even if it wasn't contained in a unit circle, even if this was a really long side, the longest will always be the slanted side, which is B, the hypotenuse. So that would just be B right there. Okay? Now let's just do with cosine. Adjacent over hypotenuse. So basically you take the adjacent side, which is D, and you do it over its hypotenuse, which is capital B. And this is the same, because we've already discussed that hypotenuse is the longest side on the triangle with its two legs connected to it. And then now let's find the tangent. Tangent is actually opposite over adjacent. So it's going to actually be opposite over adjacent. So opposite here would be A, like the same thing right here, and adjacent would be D, the same thing right here. These would be the core ones for this. Now let's do it using the green way, and let's see if there's anything different we notice about how we did it. So let's go back and just do sine of the green thing. Well, green theta if you want to call it. So we know that sine is opposite over hypotenuse. So opposite, we're at D. Hypotenuse, we're at B. Cosine theta, which is adjacent over hypotenuse. Adjacent of the green is the side that's touching it directly. We want the side that's touching it. That'd be A. Hypotenuse here would actually be B, right there. Remember, it's the longest side. Now let's do the tangent. Tangent would be opposite over adjacent. So opposite all the way down through here over its adjacent. Remember, we said opposite, and we've already defined it actually previously. It's opposite already being D. And looking back and seeing this, we know adjacent is going to even be A. Now this is something pretty cool to notice actually, if you think about it. So these two are the same. These two are the same. And these two have fractions that are just inverses of each other. So flip them around. Inversely proportional to each other. So if you just like flip around the D and the A, then you'll get those. So that tells us two things. That placement of theta is super important. You have to look. You have to ask yourself, where is this theta located? Because it's not always going to be located there. Sometimes they can locate it right there too. I'm just going to tell you right now, theta is, I've never seen in my math career life that theta has been ever placed here at the right angle of a right triangle. So, yeah. Remember, this can only work with right triangles though. Well, it can work with any triangle, but I don't want to get into too much of laws of sines and laws of cosines and such like that. But I've never seen theta placed, period, in a right angle. So you have to ask yourself, where is theta located? You also have to ask for, what are they looking for? Are they looking for sine, cosine, or tangent? Because these three things give you different examples of what they would be looking for. Like if they're asking for sine, it'd be opposite over her hypotenuse. So it's like, you can remember like so, ka, toa. That's another saying they have. If you want, you can memorize it by this. If you just memorize these formulas, then you'd be good. But you can also memorize it by so, o, like oh, like OH, ka, like the C, the A and the H, toa, so the T and the O and the A, as a way to memorize all these things. Now let's clear this board. I'm about to show you something that's a little bit different, than those functions. So we've already established sine of theta. But what if I were to tell you there is something that also equals sine of theta that's inverse like that? And that is cosecant. Now, we also have cosine. 1 over cosine of theta is secant. And tangent of theta, which is 1 over tangent, equals cotangent theta. So basically, if we said sine was remember that opposite over hypotenuse, cosecant would actually be hypotenuse over opposite. And if we know that cosine is going to be adjacent over hypotenuse, then and secant, these terms are tongue twisters. Secant would be hypotenuse over adjacent. Now we said tangent was opposite over adjacent. Cotangent would be adjacent over opposite. Now here's what I say. I say the best thing for you to do is to actually just stay core and just memorize only these three. And then then all you do is just take it over whatever the trig function you want to use. So you can get these. It's a lot easier if you were just to memorize these. Just take 1 over that trig function and you'll automatically get that. So there's no need to memorize any of these things. It'd be smart to just actually just do it this way. Memorize this, take 1 over that, you already know what that is. And before we finish up this lesson, I want to discuss a special topic in math using triangles that also relates to the unit circle we just saw. So this is going to be a little bit different. So we have special right triangles, and I'm just going to do this using 1, starting off with a base of 1s, because it's a lot easier to visualize and see special right triangles when you're just doing it by 1. So for the first one, we have 1 square root of 2. Second one, we have square root of 3, 1, 2. And then for the third one, you have square root of 3, 1, 2. Let me give you some characteristics. This is at 45 degrees. This one is at 30 degrees. And this one is at 60 degrees. More characteristics. And if you need to, this is a ratio, so the ratio usually holds as this. And Pythagorean theorem actually works for this. Now, if we're looking at this in radians, this would be pi over 4. This would be pi over 6. This would be pi over 3. Now, what special right triangles develop is an easy way for you to calculate things. So I'm going to draw like a little example here on the top here. So let's just say I was given in this example, I was given 8, 8, and I need to find what question mark equals. Well, since we know the ratio is 1 square root of 2, I can just do 8, 8, something with the square root of 2, which is going to be that 8 right there, to complete that side. So actually, this would just be 8 square root of 2. And the same ratio would hold for there if I were to do it on a different problem. If I was given, I don't know, 9 times the square root of 3, and I was given a 9 here, then this side would be just 18. Draw that out, actually. That's actually a good example. So that would be 9 times square root of 3. 9 over here, we're keeping the same ones here in the same place. This would just be 9 times 2, which just equals 18. And so on for you and for this example.